Good morning, Mr. Chan here, about to do Algebra 2, Lesson 2-4, called Complex Numbers and Operations. Please turn your student companion note takers to page 43. We have an opener here, which I believe I'm going to go ahead and skip. And we'll have to create our own opener. The name of the section is going to be pretty much new for most of you. I'm going to work around the empty space. I'm just crossing out the parts I don't need as an introduction for the section. I'm just randomly crossing out stuff and just focus on the white parts, the empty space. So, complex numbers and operations. When I was a student, I was confused why we have different number systems. Once in a while, I would hear, especially in middle school, oh, the solutions are real numbers. And I thought, what? What does that mean, real numbers? Isn't everything real in our lives? The word real doesn't mean like something that's actual in math. Real is referring to a type of number system that we can work with, that we use every day. This section today is about a different system that had to be created for specific unique situations. And it's not that big of a deal. So the idea of a real number system means to what we're working with right now. We will be switching to another system, and those are complex numbers, okay? And one great example of that happening is when we deal with parabolas. For example, let's get started here. We want to graph y equals x squared minus 1. We know the parent graph is a parabola. The minus 1 is your k value, which shifts it down 1 unit. Quick draw of that, you'll get a graph that looks like this. Right? When it crosses the x-axis, you note that there are two solutions, one at -1 and the other one at +1. And the reason why is because at the x-axis, the y values are 0. So when you try to solve x squared minus 1 equals 0, you can solve it in multiple ways. You can add 1 to both sides and square root and get plus or minus. Or if you try to factor x squared minus 1 at difference of squares, you'll get those two solutions at -1 and +1. This is considered to have two real roots, which is kind of weird to say. Roots are also known as zeros or solutions. Okay? Two real roots in this case, two solutions. What if we change the problem to say this? Graph y equals, let's say, negative parentheses x minus 1 squared. What would that look like? Well, if you use a graphing calculator or whatever and graph it lickety split, you'll get a graph that's inverted because of that negative sign, and the h value is +1, which makes it move 1 to the right. So this particular parabola looks like this. What we want to do is see where it crosses the x and crosses the x-axis. In this case, there's only one intercept at +1, right? You can plug it in. When you set y equals 0, 1 works. Nothing else works. So this is considered to have one real root. Actually, because there's only one, this is called a double root. All right. So far we have two real roots, one real root. And the third possibility is what happens if you want to try to graph this one? Y equals x squared plus 2. It's kind of similar to the first example we just did, but this time instead of going down, I'm going to go up 2 units because of that k value with the parent graph. When I do that, I have a parabola that kind of floats above the x-axis. In fact, it doesn't cross the x-axis, does it? This is considered to have no real roots or no real solutions. I will use the word roots, zeros, and solutions interchangeably. So at this point, you're thinking, oh, there's no real solutions. But here's the clincher. They created another system that allow you to do more work, more math. It's actually linked to aerospace engineering, electrical engineering, electricity, and so on and so forth, that this is required. It's not necessarily in our own world, but I'm just going to tell you now, it's not a big deal. It really isn't. You just have to know one particular thing about real roots. The thing about parabolas is that when you try to square root, because if you take that problem right there and try to solve that, right? 0 equals x squared plus 2. If you try to move the 2 to the other side and solve it by square rooting, the problem is trying to square root a negative is problematic in the real world. Yeah? Make sense? So trying to square root of it, a negative number is, uh-oh, womp, 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 womp. This is considered to be illegal in the real world. So what did they do? They defined something new. So over here on the left, write down the square root of a negative number is the focus of the section. Normally, on a calculator, you would get an error in the real number system. Calculator, real number system, you'll get an error. Okay? So what do? We are going to have a new definition in algebra. Let's go ahead and define what the square root of a negative number is. Specifically, let's define what the square root of -1 is. Write this down. The square root of -1, we'll give it a letter, the letter I. I know, this is crazy. Excuse me. I stands for the imaginary unit. Another word they should not have used, I think. I know, real and imaginary, those are strange. Just pretend that they're just different systems. Don't think that imaginary numbers are fake. They're just not part of the real number system. Just pretend it's like calling it a name, like, oh, this is the chance system. We're going to define -1, the square root of -1 as I. But they called it the imaginary unit. Okay? Treat it like a variable, please. Like x. Treat I like a variable. Once you understand that, everything is very easy to deal with, as long as you remember this particular declaration. The square root of -1 is I. The word real and the word imaginary doesn't mean fake or actual things. These are just different systems, and that's it. This is part of a system called the complex number system. The name of the section. It's really not a big deal. A plus BI is a binomial containing 2 parts. A you've done for years since you were in kindergarten is the real part. When you count numbers, when you multiply numbers, those are all there. The BI part is the imaginary part. Treat this like a variable, like regular terms. It's not a big deal, okay? So let's move on and try some problems. Next page. Okay, let's write this down at the top. Just a reminder, I is equal to the square root of -1. This is called the imaginary unit. Treat it like a variable. It's part of the a plus bi complex number form, comprised, of course, of a real and imaginary part. You've dealt with imaginary numbers all your life. You just didn't realize b was 0. You just had a 0 I there, just hanging around. Now, before I do actual problems there on the note taker, I'm going to throw in my own here off to the left, please. Example 1. 1a. Solve x squared equals 16. Well, that's not that big of a deal, right? A couple of ways to do this problem, of course. You can either square root both sides. Let's do that. When you do that, you do produce a plus or minus. And the square root of 16, of course, is 4 or -4. It's one way of looking at it. The other way, of course, is to treat x squared equals 16 after you move the 16 to the other side as a difference of perfect squares. So x squared minus 16 equals 0. Aha! Difference of perfect squares. And we can factor that using our skills from Algebra 1. Well, look, x squared is xx, and 16 is 4 and 4, and the minus is minus plus, and you solve them separately. And you get the same answer as we did a few seconds ago. All right. So the reason why I did this problem with you is because just a quick reminder of how to solve this. I mean, there's a lot of other ways you can do this. I mean, you can graph if you want to the solution. See where it crosses the x-axis. You can use the quadratic formula. Remember that? Negative b plus or minus blah, 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 blah. So here's the clincher. What happens if you are trying to take the square root of a negative number? That's the problem. So let's do that. Call this one example 1b. Solve x squared equals -9. Now remember what we did for the opener. X squared minus 16 would have been a parabola earlier of shifting down 16 units. Here, this would be x squared plus 9 if you move that -9 to the other side, technically. That would be a parabola above the x-axis, wouldn't it? At +9. Just a reminder of that, just from the opener. Question is, how do we do this algebraically without having to deal with the graphing? So obviously the opposite of x squared is square root both sides. That's our next step. Aha. We don't know what to do with the square root of -9, because normally that would give us an error. However, if you separate -9 into a couple of factors here, let's do that. -1 times 9. You guys see that? And then further, to make the connection with the actual definition, this is the same as the square root of -1 times the square root of 9, like that. We all know what the square root of 9 is. That's 3. But do we know what the square root of -1 is? And that answer is, yeah, I. So ladies and gentlemen, this is not a real solution. This is an imaginary solution. Don't forget the plus or minus. Complex numbers always come in pairs. Something to remember now. there's your answer. This is considered to be two imaginary roots, or it's a complex number, okay? That's it. All the math is the same, except one little thing: the square root of -1 is I, the imaginary unit, which sets us up for number 1A and 1B in our note taker. This is pretty easy now. Let's do it. Square root both sides. Oops. Use a different color. Sorry about that. OCD kicking in. All right. Oh, 5 is not a perfect square. However, there's a negative in front of it. I can mentally separate that if I want to, as -1 times 5. 5 you can't break down further. You leave it underneath the radical. But the -1, the square root of -1, comes out as a positive, comes out as an I. So the answer is, final answer is plus or minus I root 5. Or sometimes you might see it as plus or minus root 5I. Make sure the I is on the outside of the radical. Don't put it on the inside. That would be really, really wrong. And that's it. It's very basic. You just have to understand the idea of the square root of -1. Number 1B next. Same process. Maybe a slightly different arithmetic process here. Whoops. Jumped the gun a little bit. I did it again. Ha 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 ha. All right, we're going to square root both sides. 72 is break it downable, isn't it? It's not a perfect square. We do need to break it down. -1, of course. Circling it because it can't go further. 9 and 8. 3 and 3 for the 9. 8 is 2, 2, 2. You probably know by now. And we're looking for pairs, aren't we? To come out of the radical. All right. We have a pair right here. Pair of 3s. Pair of 2s. And the I comes out, I'm sorry, the -1 comes out as an I. And we do have a leftover 2 stuck underneath the radical, okay? And let's clean that up. So again, I will take 6I root 2, or you might see it this way, 6 root 2I, like that. Either way, it's acceptable as an answer, okay? Just be careful where you write those I's. Make sure they're not underneath the radical. All right. Habits of mind. How do you know that the solution to the equation x squared equals -5 must be an imaginary number? It's because if you try to square root a -5 or a negative number, this will produce an imaginary unit or number, okay? That's all. Okay. So earlier when we started this lesson, I mentioned that I is like a variable. So pretend it's like X. We're just going to start adding complex numbers together. A plus BI. All you have to remember is that A plus BI has 2 parts to it. You have the real part and the imaginary part. And just treat them like variables. So when it comes to adding, subtracting, you want to combine like parts. That's the key. Whenever I teach this to Algebra 1 kids, when it comes to combining like terms, I say, okay, it's like going trick-or-treating and you go home after a big long night and you're sorting your candy stash. Oh, let's put all the Snickers in one pile, put all the M&Ms in another pile, and the sweet tarts in the third pile. You're just sorting things here, same thing. But in terms of numbers, this is the real part and the imaginary part. We're going to combine like parts of complex numbers. All right, number 2A. All we have here is just an addition problem. I just pretend the parentheses aren't even there. I look at the two complex numbers and I just focus in on the real part. Oh, okay, that's easy. -4 plus -2 is -6. That's it, yeah. And the imaginary part is 6i plus -9i. 6 minus 9 is -3i. That's it. I know. That can't be it, Mr. Chan. Letter B is a subtraction problem. You do have to be careful here. If you want to do a mental math here, you got to be careful. But I like to distribute the negative sign just to be safe. That's just me. Distribute that minus sign on the back half of this binomial. You'll get, rewrite the problem, 3 minus 2i, plus, because you have two negatives there, plus 4, and then minus I, okay? And from there, do the same thing as you did in the previous problem. Combine like terms. In this case, combine the real parts. 3 plus 4 is 7. Great. And then the imaginary parts, -2i and minus 1i is -3i. And that's it. Wow. I have a feeling we don't need a bunch more of those, do we? So just to summarize at the bottom, how is adding and subtracting complex numbers similar to adding and subtracting binomials? You're just combining like parts or terms. And those parts, of course, are real and imaginary. All right, we're doing pretty good so far. All right, now it gets a little more complicated. We're going to be moving on to multiplication and division next, okay? Take a deep breath. Here we go, next page. This is a lot lengthier. All right, page 45. Now, before we get into multiplication, I'd like to show you a little cycle of how to deal with i's and the definition of the square root of -1. We need to see what happens if we start multiplying i's together. So let's go in the upper left-hand corner here, create like a little pattern, okay? I is defined as the square root of -1, fine. What happens if we multiply I by itself and get I squared? Well, technically, I is the square root of -1. I squared is root -1 times root -1. The radicals go away and it becomes -1. Isn't that strange? So let's circle that. I squared is -1. Weird. Let's add another power of I to the third, and see what happens. I to the third is technically I times I squared that we just got a second ago, and I times I squared is -1. Interesting. I times -1 is -I. Isn't that weird? So far we have I being itself, I squared is -1, I to the third or I cubed is -I. Weird. Let's try another power. Let's bump it up, I to the fourth. Okay. You guys agree that I to the fourth is I squared times I squared? I squared, you know, is -1. So I'm going to replace I squared with -1 and do it again. Look at this. I squared is -1 times -1 is +1. What? What's going on here? So ladies and gentlemen, I to the fourth is 1. Let's try another power. I to the fifth. I to the fifth is I times I to the fourth. And didn't we just mention I to the fourth a moment ago? That is 1. And oh, I to the fifth goes back to I to the first. It cycles round and round. Multiples of 4 exponents. These are cycles of 4. Ooh. So they can give you an interesting problem like, hey, what if I want I to the, say, 253rd power? You're not going to sit there and go through that whole cycle, you know, I to the first, second, third, fourth, fifth, sixth. That would take forever. So the technique to simplify I to the 253rd is to do long division. Take 253 and divide by 4. Because all those powers of 4 are just 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 forever. You don't really care about that, do you? Okay, just powers of 4 are just 1. They all go away. They all disappear as 1s. So 4 goes into 253. 6 times 60. Let's take a look here. Aha. Ladies and gentlemen, 4 goes into 253 63 times with a remainder of 1. So technically, I to the 253rd power is the same as I to the 4th power to the 63rd power times I to the 1st, the remainder from a second ago. That's what that means. All those I to the 4th go to 1, and the only answer is I. That's your final answer. I know. Not too bad. So that's a quick lesson on how to do powers of I. Okay. Let's go ahead and try multiplication. These problems here are a little bit crazy, throwing fractions at you. So let's try an extra problem up the top for a really quick introduction. Here we go. Let's do 3i times -5 plus 2i. It's kind of like something you might have been given in Algebra 1. Oh, 3x times -5 plus 2x. It's just one of those types of problems. Instead of x's, just pretend they're i's. Yeah. All right. Normally in Algebra 1, you would distribute. I'm going to do the same thing. I'm going to distribute the 3i to the -5. That'll give me -15i. And then 3i times 2i would be plus 6i squared. Huh. That's kind of interesting. 6i squared can actually be simplified. Remember that progression of powers off to the left there a second ago? I squared is -1. -1 times the 6 right there is -6. Yeah, crazy. So -15i, 6 times -1 is -6. And you can't go any further because that's it. Those are unlike parts. You will see the answer like that, or sometimes you might see the answer written in complex form, -6 minus 15i. Either one's fine with us. So that is all you have to do. Let's try 3a and see what happens. Distribute. And eventually, oh, whoa, 3b is a binomial times a binomial. That's a FOIL situation, isn't it? Okay. Here we go. Zoom in a little more, right? All right, we're going to distribute, multiply 2/5 times 10. Yikes. And of course, minus 2/5 I times 5/2 I. Watch out for those negative signs. Let's reduce. 5 goes into 10 twice. Right there, that'll give me 4i. And over here, minus, Ooh, nice. 2/5 times 5/2, those all go away. Nice. Leaving with a minus I squared. Watch out for that minus sign. And I squared, you know, is -1. So clean that up. We have 4i minus 1 is +1, and rewritten in complex form is 1 plus 4i. Okay? All right. Number 3b is basically a binomial times a binomial. There's going to be FOIL, basically. Let's do it. 1/2 times 1/2. Find first terms. Outer terms are next. We have 1/2. Let's see, it's going to be a minus sign, isn't it? Minus 1/2 times 2i. The minus sign I'm just putting right in front of the 1/2. Hope you don't mind. Inner terms. Plus 2i times 1/2. Those are your inner terms. And last terms. Minus 2i times 2i. Notice I put the minus sign in the back. That's okay. Let's clean that up one bit at a time. Starting with the first term. 1/2 times 1/2 is 1/4. Second term, the 2's cancel. Nice, leaving with a minus I. Third term, the 2's cancel there too. Giving you a plus I. Interesting. And the last terms, we have a minus 4i squared. We know I squared is -1, so let's identify that. And look at the middle two terms when we FOILed it. -I plus I basically cancel each other out. They go away. Woohoo! Bye-bye. And that, ladies and gentlemen, will give me, let's clean this up, 1/4. And then on the back half, -4 times -1 is +4. And this gives me a, ooh, fractions are scary. What is that? 4 1/4? And if I convert it back into an improper fraction, I get 17/4. And that's my answer. Isn't that strange? All right. Woo. Now, this gives me a great connection to the next type of problems we have to do, and that is division, called quotients. What just happened here? When we did FOIL on 3b, the middle terms disappeared. They canceled. Question, why did they cancel? How does that happen? If you look at the original problem, 1/2 plus 2i, and the other half is 1/2 minus 2i, there's a name for those two things. Those are actually related to each other, and those are called conjugates. You may remember that from Algebra 1 when we have conjugates for radicals, radical conjugates. And something interesting, let's go off to the left here and talk about conjugates really quick. Complex conjugates. We need them. They're important. They help us simplify radicals and imaginary numbers when they're stuck inside fractions and radicals and stuff. So a plus bi, our complex number, has a complex conjugate, it's called. That complex conjugate is a minus bi. That's it. You swap the sign with the back half. When you FOIL conjugates, this is the interesting part. Like what we saw in example 3b, the O and the I cancel. And the last term, of course, is I squared, usually, blah, 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 I squared, and that becomes a -1. So when you FOIL conjugates of complex numbers, they will essentially get rid of the i's themselves. And that is useful for quotients in our next problem, okay? So remind yourself, we have to use something called complex conjugates for binomials. Here we go. Good luck. This is weird, all right? Like radicals in the denominator. We don't like radicals in the denominator, okay? And we don't like imaginary numbers in the denominator. We have to do something called rationalize the denominator. Keep that in mind. Let me zoom up a little bit. There we go. So let's make a note of that. We need to rationalize the denominator. Write that down. Rationalize the denominator. Because if we don't, having imaginary numbers in the denominator is very messy when it comes to algebra. And to do that, we need to use something called the conjugate. All right, look at number 4a. I'm not a fan so far because they could have made the numbers a little nicer with 80 and 2 and 6. I mean, right away, I already know that can be reduced. In fact, let's reduce it. Oh my gosh, that's a silly problem to start with. 2 can divide into everything, can't it? If I take out a 2 in the denominator, that will take out meaning factor out. That will leave me with a 1 minus 3i. And the 2 goes into 80, 40 times. That makes my life easier, yeah? From here, I notice that my denominator is a binomial complex number, a plus bi. Right there. I can't have that there. I need to rationalize the denominator, and the key here is to multiply by the complex conjugate. That is the key. Okay, we're going to run out of room here, so I'm going to write as small as I can off to the side here. Write down what we just got here, 40 over 1 minus 3i. And anytime I have polynomials, I like to parenthesize them so I don't get into the habit of canceling parts of polynomials. That's illegal. So take a look at 1 minus 3i. The complex conjugate of it is to multiply by the same parts, but the real is opposite. So we're going to multiply top and bottom by the complex conjugate of 1 minus 3i is 1 plus 3i. And because this is a fraction, you got to do it to the top and the bottom. Okay? That is the key right there. So you just treat this as 2 separate problems and multiply them right now, and that's it. I'd like to do the denominator first. Let's do the denominator. I'm going to do the whole thing, okay? First terms, 1 times 1. Outer terms, plus 3i. Inner terms, minus 3i. And last terms, watch out here, negative 3 times positive 3 is minus 9. I times I is I squared. Now, after a while, you start noticing a pattern when you're multiplying by conjugates. The middle 2 will go away. I by the 3i and the negative 3i. And the I squared on the end becomes negative 1. So look at that. The denominator is simply a bunch of regular numbers. We have 1 on the front there, and we have minus 9 times negative 1 is plus 9. Okay? Look at that. No more i's. They've gone away. We all know that 1 plus 9 is 10. And go back to the beginning here and distribute the 40 to that part right there. And when we do that, we will get 40 plus 120i. And, oh, interesting. Those can't be combined together. However, we can reduce it a little further after we factor out a number from 40 and 120. Isn't that interesting? In fact, don't we eventually want to reduce with the 10 in the denominator? Let's take out a 10. I mean, technically I can take out a 40, but I'm going to have to re-multiply it anyway. Let's take out a 10. Factor out a 10. That will leave me with 4 plus 12i. Great. I mean, I could have taken another 40, that's fine. But I'm already anticipating that this part will cancel. And ladies and gentlemen, there's my final answer, 4 plus 12i. What do you think? Let's take a breather here. Wow, that was a lot going on here. But the point is, we cannot have imaginary numbers in the denominator of a fraction. That is the point, okay? All right. 4b. Let's parenthesize everything. That's a polynomial. The key is to multiply, rationalize the denominator because there's an I in the denominator. The complex conjugate of -1 plus 2i is -1 minus 2i. I don't care about the real part. That doesn't matter. Ready to FOIL? Here we go. First term, -1 times -1 is +1. Oops. Color, color, color. Outer terms, -1 times -2i is +2i. Oh yeah, they go away, don't they eventually? They do go away eventually. I'm gonna write it all out. Minus 2i there. Dun, dun, dun. I know, obsessed with colors, aren't I? And then finally minus, for the last terms, 4i squared. And the I squared, of course, is -1 right there. And those inner and the outers cancel. And the denominator is 1 minus 4 times -1 is 1 plus 4, which is 5. All right, let's clean up the top first, though. The top has a binomial times a binomial. A lot of work there. Here we go. The middles don't cancel, though. These are not conjugates. 4 times -1. I know, color again. And outer terms, 4 times -2i. Inner terms, -3i times -1 is +3i. And last terms. This is crazy, isn't it? But it's just algebra. Pretend that I is like a variable x. I squared is -1 on the end there. Yeah? Let's rewrite the whole thing in the numerator. -4, we have 2 I terms that can be combined together. -8 plus 3 is -5i. And the back end is +6 times -1 is -6. Keep going. Clean up the top. Bottom is just plain 5. -4 minus 10 is -10. I'm sorry, I just said the answer. -4 minus 6 is -10 and minus 5i. Oh no, you're kidding me. You think the problem is done, but you notice you can take out a 5 in the numerator to clean this up even further. Crazy. Take out or factor out a 5 in the numerator. Oh, crazy, huh? You don't have to put the 1 there, but it's kind of nice to see. The 5s go away. Giving you, finally, a reduced complex number that is -2 minus 1i, or just I is fine. That, ladies and gentlemen, was a lot of work. All right. Thank you for continuing. Normally, I would probably stop here and probably give you guys a break and come back to this another time. I'm going to continue with the video. You can always come back to another day. Question: why do you multiply the numerator and denominator of a complex fraction by the conjugate of the denominator? Well, the point is, like any fraction, let's say we have a fraction like 1/3. If you are multiplying the denominator by a number, say 7, you got to do it to the numerator too. Otherwise, you're changing the whole problem in the first place. Technically, this is a form of 1. 7 over 7 is just 1. You're not changing the actual real problem, the original problem at all, okay? You're not doing that. So keep that in mind. You are not altering the original problem. This is just a form of 1. All right. Let's go ahead and start factoring using complex numbers. Let's move on to number 5 here. Here we go. Before we do factoring sum of squares, and you won't see a lot of these at all, I just want to remind you of something you learned in Algebra 1. Remember when we had difference of squares? Typical problem might be, oh, hey, factor this. X squared minus 9. And you notice right away it's a binomial. There's a minus sign or a difference. And it's square rootable. Made that word up, by the way. So here it is. There's a minus sign. It's a binomial. And it's square rootable, like that. Which means my answer is the product of a sum and difference. In this case, the square root of x squared is x. Square root of 9 is 3. And that is your factored form. In fact, if you look at it, these are technically conjugates. Aha! Just like complex conjugates, these are ax plus b conjugates. See the connection there? If you FOIL this, the O and the I disappear. Let's take a look at number 5 here, okay? And these two have a little slight twist because of the section. Factor a sum of squares. Now, a second ago, we talked about difference of squares. Here, we don't have, in the real world system, sum of squares. What you want to do is pretend that we're going to convert this 4x squared plus 25, and we're going to break up that plus sign to make life easier. Watch this. Pretend that 4x squared plus 25 is the same as 4x squared minus negative 25. Now it becomes a difference of squares, perfect squares. Isn't that weird? So let's put our sum and difference. All right. What is the square root of 4x squared? 2x, Mr. Chan. Nice. Hey, Mr. Chan, what is the square root of negative 25? Well, that's just negative 1 times 25. Isn't that just 5i? Isn't that a cool way of looking at it? Yeah, that's your answer. This parabola will not hit the x-axis. However, it can be factored. Very, very strange, isn't it? Sometimes they hide perfect squares. 8 is not a perfect square, nor is the 18 in the next problem. However, I can see a number buried in the number 8, like the number 4, and another number buried in 18, like the number 9, that can be found by taking out or factoring out a monomial GCF first. So let's do that. Factor out a monomial GCF. In this case, is the number 2 is the greatest common factor, leaving you with a y squared plus 9. Ha ha ha. All right, let's rewrite that as this. Y squared minus negative 9. There's a minus sign. These are square rootable. And let's create a plus and minus here. product of a sum and difference. Okay? All right, there's that 2 from earlier. Hey, the square root of y squared is y. And the square root of -9 is 3i, yeah? Ladies and gentlemen, there's your answer. Is that strange? All right. Let's jump to number 6. So we're going to factor and solve at the same time, and the answer we'll get will be real. Won't be real answers, it'll be imaginary answers. Here we go. Number 6. X squared plus 49, that's easy. Let's factor that. It's a sum of squares, or when we pretend that that's a double negative, becomes a difference of perfect squares. The square root of x squared is x. Square root of -49 is, hold on, I forgot something here. 7i and -7i. Oops. Okay. And this time we are setting it equal to 0. Split them up and solve individually. I have x plus 7i equals 0. X equals -7i is one of my answers. And the other one is like this. X equals +7i. You can combine those together. X equals plus or minus 7i. Looks familiar. Now, could you have gotten that answer just by square rooting both sides? Yeah, I'll show you that too. Either way is fine. Just to show you the connection. X squared plus 49 equals 0. X squared equals -49. Square root both sides. And there's your plus or minus 7i. Again, ha ha ha. 2 approaches, same answer, yeah? All right. Let's take care of letter B here. It doesn't matter. I'm going to actually show you both ways. It's actually good practice. I'm going to go ahead and solve this by factoring. The square root of 9x squared is 3x. Ooh, be careful. This is minus here. Minus 25. Same thing from up here. -49. The square root of -25 is 5i. And that's a minus plus, or plus minus equals 0. Split them up and solve. 4x. So I kind of did that a little faster. I hope you can follow along. Sometimes you already know these patterns of isolating x here. That's all I'm doing. And there are my 2 answers. You can solve it manually, forcing it through. Here's the other method, and you get to decide what you want to do. Let's move the 25 to the other side. Divide by 9 is next. Square root both sides. And there it is again. Yay. Wow. I think we're ready for the last page. You guys ready? All right. Whew. Long lecture. Very long lecture. All right, let's get to the last page. This is a 2-3 day lecture. Please don't freak out. Number 5, we're just subtracting here. 2 complex numbers, distribute the negative sign. Make sure you remember we're going to be combining like terms, combining like parts in this case, reals and imaginaries. Rewrite the problem after you distribute the negative sign. There we go. We have reals and imaginaries. 2 plus 6. Sweet. And 5i minus I, or simply 1i, is 4i. Yay. Next one involves multiplication. We are distributing a 2i. Let's do it. 2i times 6 is 12i. And 2i times 3i is 6i squared. I squared, you know, is -1. This gives me 12i minus 6. Rewrite it in complex form, -6 plus 12i. Great. Wow, those seemed a lot easier than earlier. Let's jump to 2 more problems and call it a day. Number 7, I don't really care. I'm going to do it 2 ways though, to show you can. I'm going to just force through and move the 16 to the other side by subtracting 16. Square root both sides. That gives me x equals plus or minus 4i. 2 answers, 2 complex answers. And over here, if I use the sum of squares technique, but pretend that plus sign is a minus -16, I can just do this, right? Square root of x squared is x. Square root of -16 is 4i. And there's your minus plus, or plus minus, doesn't matter. Split them up and solve. And there are your 2 answers right there. Almost to the finish line. Any questions? Ooh. Oh, number 8. I'm just going to do it one way, square root both sides. Who cares? It's ready to go. Ooh, can't believe I got through this. Square root of -25 is 5i. Wow. I think I'm ready for a nap. Thank you very much. I hope you understand. Ask questions in class or email me or whatever. Thank you very much. Have a good day.